Okay, now I would consider another model. This is one scenario. In the second scenario, I would consider an unbalanced line. So this is the one, an unbalanced production line with no random variation in cycle time and no machine failures and calendars. So let me simulate this scenario. So what I will do here, let me assign different cycle times. Here, say for example, 24 and 7 here, and this as high as 32 and 15 here, and here as high as 36 and 10 next one. And these cycle times are very large, so therefore I would put two machines here and activate both of them. And here also two machines, both are activated, and three machines here, all three machines are activated. But the effective cycle time at a second workstation is 12, and effective cycle time at a fourth workstation is 16. There is the bottleneck here in this example. And the effective cycle time at seventh workstation is 12 again. So let me create the resources accordingly. It says wrong resource at stage 2 here because only two machines are available. I'm activating 22, so it is an error. So let me go here, and I'm assigning right now the standard speed for all of them. And because I changed the cycle times, I have to recreate jobs. I will create 100 jobs. So I'm ready now to simulate this scenario. So let me go ahead and simulate now. So in this simulation, the average daily production is 83.38. And yeah, for every 16 minutes, we get one piece from the line. The average width on the line is about 18 pieces, and the average lead time is this. Let us see the material flow through Gantt chart. So you can see the flow of each piece through 8 workstations. So there are two, as you see here, there are two machines at a second workstation, two machines at the fourth one, and three at the third one, the seventh one. So you can see the both machines at second station, the R21, R22, they are working simultaneously. And again, after this is finished, the R2 is taking up piece P3. So similarly, at fourth workstation, both machines are working. And at seventh workstation, all three machines are working. And the yellow segment represents waiting time of the pieces. So therefore, you can see the waiting time is increasing gradually. The reason is we allowed, we set inventory limit as 5, means we allow waiting of up to 5 pieces at any work center. For that reason, some pieces are waiting, before the bottlenecks and even the previous ones. If you see here, this P20, this piece, this one, these 5 pieces are waiting for resources at fourth workstation because we allowed only up to 5. For that reason, the machine R3 is sitting idle during this time. During this time, it sits idle. Otherwise, it will send one more piece to the fourth workstation, violating that inventory limit. So you could scroll down and see the flow, but because the fourth one is the bottleneck, you would not see much waiting after that. Let me show you the material flow, for all 100 pieces. So you can see here, each thin horizontal line represents the flow of one of the pieces. The horizontal yellow bars represent waiting times. And now, when there's no random variation in cycle times, we can release the pieces to the first workstation at optimal times so that the pieces do not wait anywhere. It's almost like a one-piece flow. So I'm going to do that now. For that purpose, I had to run a different algorithm rather than pull. Here's a pull with no waiting time, basically. So let me simulate the scenario. Let us look at the workflow. You could see here, each piece is released at the right time to the first work center so that that piece does not wait anywhere. So note that the cycle times are different, the number of machines varying with work center. In spite of that, we can release every piece at the right time so that the piece does not wait anywhere. This one piece flow in this unbalanced line. But I cannot do that if there is any random variation. So this is the second scenario. So now let me every experiment is recorded here. This you see the output simulation output summary. Each row corresponds to one of the experiments. We did so for 5 experiments, but you could also see you open this window to see both input and output for every experiment. For example, the first experiment, the inventory limit is 5, cycle time is 10 everywhere, and standard speed, and there is a resource utilization. These are the output of the simulation. And the second one that you can see in the input and output, you remember that I delayed the R4 for a while, and third one likewise you could see, so that you could analyze. You can go back and analyze every experiment using that window.